going over free body diagrams. Free body diagrams are just a simple diagram that shows every force that is acting on an object. From that, you can add up the forces to show what the net force is, or you can make the forces appear to do what the object should be doing. So with that, we're going to go over some stuff that we went over a long time ago about vectors. So remember, when vectors are in the same direction, we can add them, but when they are in different directions, we subtract them. In this case, we will be subtracting them, such in situation A. So we have up and we have down, so those subtract to get 0. And we have horizontally, we have left and right, which give us 0. So the net force on this object is 0. Now on B here, vertically, 3 minus 3 is 0. But horizontally, we have 5 newtons. That's 5 newtons left. Because remember, vectors have a magnitude, as in the 5 newtons, and a direction, left. Alright, C. We just have vertical arrows, so we subtract. 20 minus 20 is 0. So the net force is 0. And in D, 40 minus 25 is 15 newtons, and that will be, alright, so F sub n is just a different way of saying net force is 15 newtons, and it's going to be up. So this object is apparently rising. So, okay, with that, we're going to go on to the next set of problems. It's basically net forces. They're going to give you the net force at the bottom, and you have to figure out what the other two variables are. So this net force is 0. So to make it all 0, we need 200 newtons at B. And at A, to cancel out those 50 newtons, we need 50 newtons at A. So 50 minus 50 is 0. 200 minus 200 is 0. Okay, here for the second one, it's going to be a net 900 newtons and up. So we need to figure out what C is. Now you can either just do it in your head, or you can actually do it algebraically, where C 900 is equal to C minus 200. So you add the 200 to both sides, and you get 1100 newtons for C. So you can just do that easily. Alright, for the next one, we have a net force of 16 newtons, and it's going to be the left. So it's going to be pulling to the left. So we know the force of gravity and the normal force are going to cancel, but the left is going to be 60 bigger than D, so we know D is 20 newtons. Sorry about my N. Okay, with that, I want you to solve this one for me and put it in your answers. You also will have a copy of this worksheet to go along with this video. So just go ahead and just submit this in the comments, or scan it and submit the answer to this one. So this will be your number 1 problem to do. And it will be 30 newtons to the right. which means you don't have to worry about F or H. They're going to cancel out. You just have to find what G is equal to. Okay, with that, we will turn this over, and we will begin drawing our own free body diagrams. I'm sorry. So, you can either start them with a big circle or a box. Now remember, the forces we've worked with so far have been normal force, which is force that opposes gravity, the force of gravity, the applied force, which is force applied, and of course friction always opposes the force applied. I'm sorry, I almost wrote, and this is friction, not applied. Now these two can swap, but it's kind of hard for gravity not to be pulling down. Okay, so a book is at rest on the tabletop. So to put this simply, we'll just go ahead and put both of these. So we have the normal force pulling up on both of them, and we have force of gravity pulling down the same amount on both of them. Now remember, anytime you have anything that is at rest or is moving at a constant speed, the length of our vectors will be equal. So the length of the arrows are equal because our net force is equal to 0. So if our net force is equal to 0, the object is either moving at a constant speed or it's at rest. If it's accelerating, then that will be at the time you will have different sized arrows. Alright, for this exercise, you can for every one you can have normal force and force of gravity, but don't worry about that unless it's something that's actually being suspended or falling at a constant velocity. If it's being pulled rightward, leftward, then worry about horizontal arrows. So just like in this one, suspended motionless from a bar which hangs from the ceiling. Alright, so basically we have the girl right here. We have the rope pulling her up, which is the normal force. And we have the force of gravity pulling her down. And they're both normal, they're both the same length because she's not moving. Okay, so an egg in a nest is free falling. So we have it free falling, which means it's actually accelerating under gravity after it falls from the tree. So here's our egg. Alright, it's being held up by its normal force, but it's accelerating under gravity, so our gravity arrow is going to be longer. There's no leftward or rightward force, but notice that this arrow is longer because it's actually accelerating under gravity. Okay, so leads us to number 6. A flying squirrel is gliding from a tree to the ground. So it's going straight down at a constant velocity. So remember, constant velocity, arrows are equal. So this is moving under normal force. It's pushing up, opposing gravity, which is the same length because it's moving at a constant velocity. Okay, so finally we have some horizontal forces. A rightward force is applied to a book in order to move it across the desk with a rightward acceleration. Consider frictional forces, neglect air resistance, draw, and the free body diagram is going to look like this. So we're applying a force to move it to the right, so that's our force applied. Friction is opposing it, but not at the same amount or greater because it's accelerating rightward. So that's the force of friction. And that's basically all we need. We could put the normal force in and the force of gravity in, but they're just going to cancel each other out and won't really matter in anything. So, but remember, it's accelerating rightward, so our net force will actually be, I don't know, just a number of newtons right, if we had numbers next to it to figure it out. Okay, so that's these drawings. All right, and for extra problems for y'all to work on, I'd like for y'all to do number 8. Keyword here that's really important right there, constant velocity. All right, student with the backpack. Skydiver is descending with a constant velocity. Considering air resistance. So basically, I'll go ahead and do this one for you. We have the force of gravity pulling it down. And you also have the air resistance. Force of the resistance is equal to the force of gravity. That's why it's moving at a constant velocity. All right, 11. All right, this one has rightward acceleration. Number 7. And number 12 is a nice little case. Car is coasting to the right and slowing down. I want to see how y'all do on this one. So you'll draw out a free body diagram for this situation. So it's going to be horizontal. But it's going to have an applied force and a friction force. But it'll be a special situation. Okay, so that has been our intro here into free body diagrams. This is less meticulous, not so many equations to do with it. Later there'll be equations that go along with it, but for now I just want you all to get used to working with these. So go ahead and do this one on the first page that I left you with, and then work number 8, number 9, we did 10, work number 11, and then see if you can figure out number 12. Okay, well that's it from me. You gotta take it easy out there, stay safe. Remember, it's a 4-day week, so this week will be kind of crazy and kind of quick. All right, so I will see y'all in tomorrow's lecture.